Hello and welcome. SFU Math 232, it's Brenda speaking. We are here, section 7.9, our second to last lecture, the penultimate lecture, Orthonormal Bases and the Gram Schmidt Process. So let's just say a couple of things about the orthonormal bases. They're easy to work with. They simplify calculations. So basically these are easy to work with. So it is sometimes a good idea to have a orthonormal basis for your subspace. Every non-zero subspace has an orthonormal basis, for example, the standard basis. Okay, so let's just make sure we know what we're talking about. We'll call out that if we have a set of vectors in Rn, they are orthogonal if every pair of vectors has a zero dot product. Every pair of vectors is orthogonal, so that's what we're checking right here. A dot product equals 0 for every pair. That's when, but that does, and then that is not vi dot vi, but every unique pair that you pick out from the set, the dot product is 0, and they're orthonormal if the dot product of vi dot vi is equal to 1. And we've actually said this differently. We have said that the vectors are orthonormal if they're orthogonal, and if all the lengths of the vectors is 1. So if their norm is 1. Okay, so let's just take an example, and then what we're going to see is if we have a subspace for which we have a basis, we're going to figure out how to change that into an orthonormal basis. That's the idea here. Okay, so let's just get at what does an orthonormal basis of Rn look like? Well, I mean, the easiest example to give is the standard basis vectors. So that would be like this: 1, 0, like that, 0, and then that would be v1, and then you would have v2 with the 1 in the second place like that, and then a bunch of zeros. You keep going like that, and then you get to the last one where the 1 will be. Those will be all zeros, and then there'll be a 1 there in the last position. So for these vectors here, it's an orthonormal basis for Rn. We have n vectors, and each vector has n components. These are the standard. These are the standard basis vectors, and they are an orthonormal basis. So you could, if you wanted, at least, I don't know, in R3 or something like that, or R4, you could check that all of the lengths are 1. That's not going to be too hard to do. And then you could check that all the dot products are 0 of any pair. Okay. And we've also seen something pretty similar to this. That is, if we have an orthogonal set of non-zero vectors in Rn, they are linearly independent. We haven't seen it phrased quite like this, but I mean, there's been other theorems similar to this. So let's just say it again. We have an orthogonal set of non-zero vectors in Rn, then we're guaranteed that they're linearly independent. Okay, so let us just see why this is the case. Let me just take any orthogonal set in Rn. Okay, and let's just call that S, some set of vectors, v1, v2, that vk. There's going to be k vectors in the set, and for sure we know that k is less than or equal to n. I mean, we're not going to be able to have more than n orthogonal vectors, and we also in fact already know that we can't have more than n linearly independent vectors. So we have some set of vectors. There's k of them, and they are orthogonal. That is our given. They're orthogonal, and be careful when you read this, right? Like if it says orthogonal, they're orthogonal. Don't assume it's orthonormal. So you have to be careful that you don't overread the hypothesis of the theorem. Okay, so to show that v1 through vk are linearly independent. So to show linear independence, well, we'll just actually go right back to the definition. We need to show then the definition of linear independence. If I take T1 V1 plus T2 V2 plus, and I go the whole way, and I get the last one, TK VK, and we have those scalars T1, T2 up to TK that we can choose, and we want to choose them such that this linear combination is 0. If V1 through VK are linearly independent, we need to show that this can happen only when T1, T2, etc., TK is 0. There's no non-zero way that this can happen. So that's, if we can show that, then we have shown that these vectors are linearly independent. So what I'm going to do then is just imagine take any one of the vectors in S. So take Vj in S, and then take this expression here, and you do the dot product with Vj on both sides. So I'll get that T1 V1 plus T2 V2 plus dot 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 plus TK VK, and then I'm going to dot product here Vj, and then on this side I'm going to dot product 0 dot Vj, and that's just going to be 0. Okay, so now let's look at this. Consider this here. I take Vj and I dot product, I distribute this in, and I take the dot product of V1 with Vj. Now if j is 1, then I'll get something. But if j is not 1, then I know that the set is orthogonal, so that will mean that V1 dot Bj is 0. And in fact, the only one that won't be 0 will be whichever vector in here is Bj. So the result of this dot product, because of the fact that V1 through Vk are orthogonal, the result of this dot product is Tj Bj dot Vj. And on the right hand side, we know that's equal to 0. We know that this is not 0, so then that tells us that Tj is 0. And you just do that for everyone. You just imagine j running from 1 to k. Do for all of them. And that tells you, do for all j equals 1 through k, and that will tell you that all of the, that tells you that T1 through tk is equal to 0. And that's exactly what we wanted to show. So that does mean that any orthogonal set is linearly independent. All right. Now, it is going to be much easier for us to do an orthogonal projection using orthonormal bases. Okay, and we can check if a n by n matrix is orthogonal. You'll perhaps recall this by taking A transpose times A and checking whether that's equal to I. So that is a quick check, especially on a computer. You have your matrix, you just multiply the matrix times the transpose times the matrix itself. You see, does that equal I? So that's a quick check. No, there's no Gaussian elimination. Okay, so if a matrix is orthogonal, that's identical to saying that the column vectors form an orthonormal set, the column vectors. Okay, so I'm just going to redo an example from the textbook in a slightly different way. So this is in the textbook, page 407. They have 3 vectors, V1, which was equal to this guy here, 3/7 minus 6/7, 2/7, and then V2 equal to this guy here, 2/7, 3/7, 6/7, and then V3 equal to 6/7, 2/7, and minus 3/7. And in the text, they show that this is an orthonormal set by taking the dot product V1 by V2, the dot product V1 by V3, and the dot product V2 by V3, and then they check the length of V1, they check the length of V2, they check the length of V3, they find out all the lengths are 1, all the dot products are 0, they conclude correctly. It's an orthonormal set. Okay, so that's fine, and that's good. And so I'm just alerting you to using this method here. What we could do is take, form the matrix A by putting the vectors in a column. The column vectors of A form an orthonormal set. So if the matrix is, so I'm looking at the column vectors for as in A. So I put the these vectors in as column vectors, and I get, what do I get? 3/7, 3/7 minus 6/7, 2/7. And then I get, put the next one in, 2/7, 3/7, 6/7. And I get the third one in, 6/7, 2/7, and minus 3/7. Okay, and then what I can do is, that is A, and then I can form A transpose here. And so I reverse the rows and columns, and I get, what do I get? 3/7 minus 6/7 and 2/7, minus 6/7, 3/7, and 2/7, and 2/7, and 6/7, and minus 3/7. Okay, and then I do this multiplication. And I see what happens. And I'm just doing the first one in my head. I'm getting 9 plus 36. 9 plus 36 is what? So I just have to write this down, I guess. 9 plus 36 plus 4. Something is, that gives me 45. That gives me 49 over 49. That gives me 1. Okay, so I do this complete multiplication, and I get this. Just kind of check the first one. Okay, I get that. I get I. So I know right away that the matrix A is orthogonal, and then that tells me that the columns of A form an orthonormal set. And then this is a second way of showing that these three vectors are orthonormal. Okay. Here's another example. We got 3 vectors, and then we get told to let A be the matrix with those vectors as a column. Not looking like this here, 1/3. This is V1. And then we have V2. And V3. Okay, there's A. And then we know we're going to need this, so let's just write it down here. We got A transpose. That looks like this: 1/3, 1/3, 0, √7 over 3, minus 2, square root 2 over 2, √2 over 2, 0, 0, 0, 0, 1, 0. Okay, so we got A and A transpose. And then what we do is we take, we're going to do this step here. This is exactly what we did above. We take A transpose, we multiply by A, and you then see that you'll get this. I mean, I did this using Wolfram alpha. Okay, you get that. And it's a 3 by 3 matrix. So notice it's a 3 by 3 matrix, and we had 3 vectors that we're attempting to check for if they're orthonormal. You can notice that what this represents here is V1 dot V1. What this represents here is V2 dot V2. And what this represents here is V3 dot V3. We then can conclude here that the V1, V2, and V3, the span of V1, V2, and V3 are an orthonormal basis. Okay, now I just want to point something out here, what can go wrong here, and that is you could multiply A times A transpose. So I did that, and this is what happens. Notice the size of the matrix. We don't have square matrices, square matrix here, so we get something that's a different size multiplying this way. God, there's lots of numbers here. Okay. Hopefully, if I haven't copied that out of Wolfram Alpha wrong, that is A transpose. So this doesn't tell you, you want to be careful because you don't want it. So I'm just going to put here careful. So if you do it this way, then you might conclude, oh, it's not orthonormal. So some amount of caution. And one way of possibly seeing that is we ended up down here checking this one, with a 3 by 3 matrix, we were checking 3 vectors. And so this one here is a 4 by 4 matrix. It's the wrong size. So we can't have here, for example, v1 dot v1, v2 dot v2, v3 dot v3, and then what would this be? v4 dot v4. We don't even have a v4. So if you make this mistake, doing it the wrong way, sometimes you can catch yourself, like your error detector corrector system goes off and you're like, uh-oh, something is wrong, the size is wrong, and then you can maybe recall, oh, it's supposed to be A transpose A, because it is easy to make that mistake, to multiply in the wrong order. And as you know, matrix multiplication does not commute. Okay, next thing, yeah, a simple formula for orthogonal projection. So we've already seen how to do a projection onto a subspace of Rn. And so, but if we now step back and look at what happens when we have an orthonormal basis for the subspace onto which we want to project, things get easier. So we take a matrix M whose column vectors are an orthonormal basis for the subspace. And then we have this, we've already seen this before. This is the projection of X onto the subspace W. So this formula can nicely simplify, because if M is a matrix with column vectors that are an orthonormal basis, so this is key, and this simplification is not going to work unless that condition is met, then this product right here, we've just seen, M transpose M, that will be I. And then the inverse of I is I. And then multiplying by I doesn't do anything. It leaves everything unchanged. So then we can simplify the projection onto W of X as M transpose X. That's quite nice. I mean, that is quite easy. You just simply take the vectors, that's the vectors that span the subspace. You put them in a matrix, you take the transpose, you do one matrix multiplication, you multiply by the vector, and you're done. You've got the projection. Okay, so then we could say also that that is the projection of X onto W, and also that if we identify this matrix M transpose, then that is that guy right there, P, that matrix P, that is the standard matrix for orthogonal projection onto a subspace spanned by the columns of M, where those columns form an orthonormal set. So that greatly simplifies. If we were going to be projecting a whole lot of different vectors onto W, we could simply store this product, and then all it is one, to do the projection, all it is one matrix times vector multiplication, and we've got the projection. Okay. All right, so now we're writing the same thing. And now we're here. We've got the orthonormal basis. Okay, then we can actually rewrite the projection here, and we can replace. Well, we can do it that way above, like with the matrices, but we can also write it this way. You take the dot product of x with v1, and then you multiply by v1. This is, of course, a scalar. So that's a scalar times a vector plus a scalar times a vector. So it is a linear combination of the basis vectors, and the coefficients here, these scalar constants here, we can find via the dot product. So that's if it's orthonormal. If it is only orthogonal, we still have an easier way of doing it, but we have to, we do basically the same thing, except that the only difference is we're dividing through by this, and that's to fix the length problem so we don't get any scaling issues. So that fixes the problem that, like for example, this one, that v1 might not be of length 1, because but they in this case are still orthogonal. They're just not necessarily orthonormal. Okay, how do we see that this is the case? Well, let's take a look at how we already know that we can project this way, like that, as m transpose x, like that. So for the first one, when we're looking here at it being an orthonormal basis, the columns of m, the vectors that form the columns of m are the orthonormal basis for w, then we write, we will write m are these columns, v1, like that, v2, these are the columns, vk. And then, of course, m transpose is are those things as rows, like that. Okay, and then we can do this multiplication, this thing here. Let us first take m transpose and multiply it by x. That's going to look like this. M transpose, v1, v2, like that, down to vk. We're going to multiply that by x. And that then will be here, v1 dot x, the dot product of v1 and x, and then this will be v2 dot x, etc., all the way down to vk dot x. And then, of course, a dot product, it doesn't, order does not matter in the dot product, so I could write this like this, x dot v1, x dot v2, like that, down here to x dot vk. All right, now I'm going to take this guy here, and I'm going to multiply by m on the left. So this will be m multiplied by n transpose x, where this guy here is m transpose x. Okay, so I go ahead and do that, and then that looks like this. v1 is here, v2 is here, like that, vk. And then we multiply here x dot v1, x dot v2, all the way down to x dot vk, like that. And it doesn't seem immediately obvious, in fact, that we're going to get this, I didn't think so anyways, that you're going to get this result here, because it doesn't look like this thing times v1 from doing this. But let's just write this out in a little bit more longhand notation. I'm now looking at the first, I'm going to now do the usual proper matrix multiplication. I'm going to take this first row here and take that into this column. Okay, and what do I get? Well, I get v11, the first component of v, and that's going to be times x, multiplied by x times v1, and then it's going to be the first component of the second vector, and that's going to be multiplied by x times v2, and I'm going to go across like that the whole way. And then I'm going to go and do the next multiplication, which is going to be the next row here multiplied by this column again, and that's going to give me v12, that is the second component of v1, x dot v1, like that, plus the second component of v2. And then I imagine adding them this way. Yeah, representing them this way. So then what does that look like? That looks like this. X dot v1, like that. And I take all these guys here, and that is just simply v1 plus, and then I've got the similar thing here, x dot v2, and that's multiplied by v2. Okay, these things here are scalars. Then I finish up. Okay, so you can see how that comes about. Okay, I'm going to do a example here. We want to find the orthogonal projection of some vector x, there it is, onto a plane that is spanned by two other vectors. Right away, I'm looking at it. As you can see, it's not orthonormal right away because, well, there's no way the length of this is 1. So it's not orthonormal. So first thing I may think to do, first thing I am going to do is put these spanning vectors into matrix M as columns. That's going to be 0, 1, minus 4, minus 1, 3, 5, 1, 1. And then I can write out the transpose. 0, 1, minus 4, minus 1, 3, 5, 1, 1. Now, there's only two vectors. I could take the dot product. That would be fairly fast to see if they're orthogonal. Just going to show you how these whole things come together. So I take the dot product. That's going to be 0 plus 5 minus 4 minus 1. That's 0. Okay, so this W1 and W2 are orthogonal basis, but they're not orthonormal. Okay, so let's just multiply. I did this Wolfram alpha M transpose M just to see what happens. 18, 0, 0, 36. Okay, so these entries here are telling you that it's orthogonal, and then the fact that these entries here are not 1 tells you it's not orthonormal. So you can't just go with M transpose M, M transpose times X. So in general, we will recall that the projection onto W of X is equal to M transpose M inverse M transpose X. So in this case, we could just go ahead with that if we wanted, and then we would simply have just a whole pile of calculations to make. That would be 0, 3, 1, 5, minus 4, 1, minus 1, 1, 18, 0, 0, 3, 6. That's going to have to be inverted. Then we would multiply by M transpose. And then we would multiply by X. That is our answer. I'm not going to go ahead and make all those calculations here, but that will work. So this will be that, whatever the projection onto the subspace W of X. That will be it. Okay, that's one option. What the other option to do would be to make W1 and W2 of length 1. So I could then say, oh, well, okay, let me, before starting up this little process, let me take W1 and maybe I'll just call this W1 bar, and that's going to be the unit vector. And so I'm going to divide by the norm of W1. What is the norm of W1? I got 3 root 2. So I just write that here. Here's W1. The norm of W1 equaling to 3 root 2. So let me just make sure. So I square 4, I get 16, 17, 18, square root of 18. Yep, 3 root 2. Okay, so I've got that, and I might as well just do this one while I'm here. The norm of W2 is 6. Okay, so I can then write out 0, 1 over 3 root 2, minus 4 over 3 root 2, and minus 1 over 3 root 2. And I can put W2 this way. And then I can calculate the projection in this manner. The projection onto W of X will simply be MM transpose. What is M? M is the column vector, so that is going to be this, 0, let's keep going, and then that's going to be 1/2, 5/6, 1/6, and 1/6, and then I put the transpose. Okay, and then I would take that is M transpose, and I would multiply it by X. And X is 1, 2, 0, minus 2. Okay, so both of these should give the same answer. You could see that were you to notice that they're orthogonal and then just perhaps make them orthonormal, now you've reduced down the calculations just to doing matrix multiplication and then multiplying by a vector. Here you've got now you have to do an inverse, then you've got to do 3 matrix multiplications and then multiply by a vector. Okay. Now imagine that we do have an orthonormal basis for a subspace, and we have some vector in the subspace. We want to express that vector as a linear combination of the basis. So we know that M, looking like this, B1, B2, like that, BK, those vectors, this is a orthonormal basis for W. Okay, we know that little w, the vector, is in the subspace. What does that mean? That actually means, this guy means that the projection onto W of W is equal to W, right? Because the thing is already there. So when you project it, nothing happens. It's itself. Okay, so what we're being asked is to express W as a linear combination of the basis. That means what we want to do is set up W as C1 times V1 C2 V2, etc., like that, CK VK. That's what it means. Express W as a linear combination of the basis vectors. Now, our question here is, the question is, what is C1 through to CK? Now, observing this, that allows us to say we can easily, in fact, represent these scalar constants here in this manner, in a very straightforward manner. So you go, maybe I'll just do a second one since it's so exciting that we can do this. So that is W dot V2, and then you're multiplying here by V2. Okay, bearing in mind that this, of course, this is C1, this is C2. These are scalars. And then all the way through to the last guy. So that actually makes it easy to find out what these constants are. Again, it is hopefully speaking to you, this saying that, oh, if we have this orthonormal basis, there's a lot of things that simplify and make it easier for us to do some of the things that we typically do. Oh, these are all the scalars. Okay. All right. Now, so that leads us to the problem of saying, well, these orthonormal bases look quite nice. How would we go about finding one? Let us just imagine we're given a subspace. The subspace is spanned by some vectors. Those vectors are not orthonormal. And we're going to be working with this subspace a lot. So rather than make more complicated calculations all of the time, we say maybe it would be a nice idea if we could take the basis that we're given and we could somehow make it orthonormal And then after that, many of our calculations and manipulations will be simplified. So that's what this is all about now. That's the final point in this lecture, actually. So the theorem is that every non-zero subspace has an orthonormal basis. Okay, fine. But what's more important about this in some sense is that the proof of this leads us to a method for taking a non-orthonormal basis and turning it into an orthonormal basis. And that process is called the Gram Schmidt orthogonalization process. So this is a type of constructive proof. It's like I'm telling you that this exists, and you say, okay, prove that to me. You're like, okay, I'll prove it to you. Let me make it. And since I can make it in every case, it exists. Okay, so this is constructive proof. So I'm not going to, I mean, this is not, this is laid out like this, but really what I'm going to do is first go through these steps, make a couple of comments. I'm going to draw a picture of this in the R2 case, which is to try to make it obvious what's going on. And then we'll go through an example of making the calculations and seeing how to do this. Okay, so the idea behind this is first you make the basis orthogonal, and then after that you make it orthonormal. Okay, so let me just somehow note that thing. So first you make it orthogonal, and then make it orthonormal. Okay, this part is easy, right? Because you get some vectors, you get a bunch of orthogonal vectors, and then they're not of unit length, and you simply just divide through each vector by its norm, and then they are of unit length. So this is the easy part right at the end. Okay, so what's going to happen in this process is we are going to have a basis given to us. So those are our W's. We're given a basis. There it is, right there. We're given a basis. The basis, this is not, in general speaking, it's not orthonormal. We have nothing to do. Okay, it's not orthonormal. And what we want to do is find a orthonormal basis for that subspace. Okay, and this is the procedure that we will follow, and I'm going to show it in the two-dimensional case so we can see what's happening. What we're going to do is we're going to assign V1. So V1 through VK is going to be our orthonormal basis when we're finished. So our first vector, we're just going to select to be equal to the first vector. And then what we want to do is we want to keep adding, like when we add V2, we want to make sure that V2 is orthogonal to V1. And then when we add V3, we want to make sure that V3 is orthogonal to V1 and V2. And we basically go through adding up adding a vector at each step, and each time we add a vector, it is orthogonal. And then once we get to the end of that, then we make them orthonormal. Okay, so what we're doing is in this step is we're saying that for each, this is going to go round and round, right? We have V1, then we get V2, then we get V3, like that. This is a repetitive step until we're complete. So we assume that, well, I mean, we start with V1, it's orthogonal, so there's only one vector. And so then we're going to be adding V2. And what V2 is, how we get V2 is we project W2 onto the subspace, the orthogonal complement of the subspace spanned by the vectors we already have. Okay, so this here is, we calculate Vi plus 1 as this projection, and that looks like this, W I plus 1 minus the projection W onto Wi of W I plus 1. Okay, this is the subspace spanned by the first I vectors. Okay, let's draw a picture. I think when we draw a picture, take care to maybe after stop the video and draw yourself the picture in 2D and say, oh, okay, I see what's going on. And then it doesn't, at least that's how I like to work. Then it won't bother me making all these calculations going, you know, I have no idea why these calculations work, but they seem to. That's a non-preferable way of handling the problem. The best way is to say, okay, I'm going to look very carefully about the geometry in R2, and I'm going to see why this works. And then once I see why it works in R2, I can see that, oh, I'm just repeating, and it doesn't matter how many dimensions I go up to, I can see why this is working, and then I feel happy making all the little calculations. Actually, I don't feel that happy making all the calculations. If I had to make these calculations very often, it would not be long before I wrote a computer program to do them. But we would do one of them by hand so that we can see what's going on. Okay, so let us just imagine the subspace R2. So we're taking subspace R2, and it's going to be spanned by two vectors, W1 and W2. Okay, R2 spanned by W1 and W2. And now what we want to do is we want to get we want an orthonormal set V1, V2 that spans where the span of W1, W2 is equal to the span of V1, V2. Okay, so here's how the process is working. Let me just show you a W1. Here's a W1. There is W1. And I don't know, let's over here make W2. They're not at right angles. They don't have to be at right angles. Okay, there's W2. Okay, now what is the subspace spanned by W1? The subspace spanned by W1 is this guy right here. That is a straight line. Good grief. Let's get that a little bit straighter. There, that's a straight line. So this guy right here, which I called capital W1, that is the span of W1. So that's the subspace spanned by W1. So what I do is I find the orthogonal complement of that, and that is going to be this line right here. Right, that's the orthogonal complement of W1. Well, actually, I've slightly got ahead of myself. What is actually the first thing I do is I choose V1 to be equal to W1. So that's my first vector. Okay, so I have V1, the first vector is equal to W1. Then I find the orthogonal complement of the span of V1 or W1. It doesn't matter because they're the same. Okay, that is this red line here. This is the orthogonal, this is the span of W, just write as V1 orthogonal complement. Okay, right. Then I project W2 onto that red line. So I take W2 and I project it this way. And I get this guy. That is V2. Now you can see what's happened because I did that. V1 and V2 are orthogonal. Okay, and that so now I have V2. V2 is equal to the projection onto the span of V1 orthogonal complement of W2. That's it. And then I have that V1 dot v2 is equal to 0. Now in this case, because I'm only got 2 vectors, I am now finished. Okay, I now have a orthogonal. I have 2 orthogonal vectors which span the same thing that W1 and W2 spanned. Now what I do is, if I want to get my orthonormal set, I take V1, I divide it by the norm of V1, and then I take V2 and I divide by the norm of V2. That gives me an orthonormal set. Okay, that's it. That is really the process. And now if there's a third one, then I find the, if I was now moving up a dimension, then what I do is I find the, I find the span, the orthogonal complement of the span of V1 and V2, and then I project W3 onto that. And I just keep building until I finish the Gram Schmidt process. Okay, so here's a statement for that. You have some basis for a non-zero subspace, and we have a corresponding orthogonal basis. And then it is also true that you notice the key thing to notice here is this is J and J, and this is K. J is assumed to come before K. So when you're partway there, you have got an orthogonal basis for the span of a portion of the vectors. And then when you add the new vector, Vj, that is orthogonal to the span of the vectors from the original basis that came before. So each time you're adding a vector that is orthogonal to the ones that came before. Okay, we're going to do the feat here of going through one finding an orthonormal basis from 3 vectors. I think I'm gonna do is I actually have all the calculations written out, but that is seriously time consuming. So I think what I'm gonna do is I'm going to write out what the calculations are, and then I'm gonna skip a few steps and write down the answer. You can work through them by hand yourself. I recommend that actually, or you could enter them into a computer and make sure that the calculations are correct. So, but more importantly is we understand what calculations to make. Okay, so we get told that the subspace of R4 has a basis. This guy here, this word here is that tells you that W1, W2, W3 are linearly independent. And we get told what the vectors are. And now what we want to do is find an orthonormal basis for W. So right now, W is equal to the span of those 3 vectors. 1, 1, 0, 0, 1, 1, minus 2, 1, 0, 3, 1. So it's a W spans R3. They're linearly independent. Okay, so we first are going to try to find an orthogonal basis, and then we'll deal with the orthonormal property later. Okay, first find an orthogonal basis. Okay, so we start the procedure. Step 1, let V1 be equal to W1. And that's, so then now we've identified V1. There it is. And that's not too hard. Okay, then V2 is equal to W2 minus the projection onto W1 of W2. And how do I calculate that? That looks like this. W2 minus W2 dot V1 divided by the norm of V1 squared times V1. Okay. All right, so now we have all the things that we need to do to calculate V2. So let us just write out what those things are. We have W2, 0, 1, 1, minus 2. We have this calculation here, so we have W2 dot V1, and we have the norm of V1 squared. And then we multiply that by V1, which we have set to this guy here. Okay, so now this is a calculation, right? I mean, this is a vector. This is some number. And then this is a vector. So we just doing one vector minus another vector, and we have to scale the second vector by the scaling constant. So there's a bunch of little calculations here. That's what I'm going to not bother to copy out. So I've got, I'm doing that calculation. I had to do it actually quite a few times before I use the computer to check, so make sure I didn't make any mistakes. So then what happens is I find out that V2 is equal, this is V2, this calculation right here. I find out that V2 is minus a half, 0, 1/2, and minus 2. So I've got two of the vectors already. I only have to find 3. I've got 2 of them already. So I've got V1, that's right here, V1, right? And now I've got V2. My strong recommendation, because you know where you're going, is to check. Now that you've got V1 and V2, you know they're supposed to be orthogonal, and if you've made an arithmetic mistake, they will not be. So it's good to check. So check quickly. That doesn't take long. You just say V1 times V2. That's equal to 1, 2, 1, 0, and then I dot that with, take the dot product with this, like that, and it comes out to 0, and I think, oh, thank goodness, right? So V1 and V2 are orthogonal. So then I can move along to the next step of the program. I then do the third vector. So that's going to be V3. And what's V3 going to be? V3 is going to be W3 minus the projection onto W2 of W3. Okay, and this here is the W2 here is the span of W1, W2. Okay, so then that is computed in the following manner. Each one that you do, of course, is going to require slightly, well, it's going to, this one's going to require, you'll see, require an additional calculation here, because I have to do V1, but now 2 vectors that I have to come orthogonal to, and then V2. Okay, there it is. So that's the calculation. Let me just write that out. That is going to be, V3, 1, 0, 3, 1. And then I'm going to take those 2 dot products. And then I'm going to take the norm. This is when you just thank your lucky stars there's computers now. Don't have to do everything by hand. And then I have to do the other one, the next one. That is going to be V3 dot V2. So this is V2. And then the norm of V2. And then I multiply that by V2. That's pretty crappy. Let me just get that. That's minus 2 there in the end. Okay, there it is. Again, it looks a bit painful. It is a bit painful to do by hand, but actually this right here is just a number. This right here is just a number. So we've got a vector minus a scalar times a vector minus a scalar times a vector. So we go ahead and we make those calculations, and I end up with V3 equal to this guy here. 2/9 minus 4/3, 22/9, and 5/9. Okay, so then I would check. This is not part of the actual procedure, but I would check V3 times v2, because you don't want to continue. If you had another one, you don't want to continue if there's a mistake, right? So you check v, so this is just a check. Check v3 dot v2, that's 0. Check v3 dot v1, that's 0. And then you're like, okay, I can move on to the next step. So right now I'm at the point where I've verified that v1, v2, and v3 are orthogonal. Okay, now the hard part of the program is finished because we only have 3 vectors in this example. So now what I do is I take v1 and I divide it by the norm of v1, and I take v2 and I divide it by the norm of v2, and I take v3 and I divide it by the norm of v3, and then I have the orthonormal set. So let me just, we've got boxed in red, we've got v1, we've got v2, and then also, why don't we just choose the red again, we also have here v3. So those are the 3 vectors, v1, v2, v3. You can confirm, I did confirm that they are orthogonal, and then now I'm simply going to make them orthonormal. And so I'll do that, and I'll just simply write down the answer. So I got that W then is going to be equal to the span of these 3 vectors, v1, v2, v3. Look at that, eh? Square root of 73. Square root of 73. 22 over 3 root 73. And 5 over 3 root 73. Okay, there it is. That is now the same subspace that was spanned by W1, W2, and W3, now spanned by these 3 vectors, and those 3 vectors are orthonormal. Now it's, I think, really happy situation that we don't have to do a V4. Because so that is the Gram Schmidt process. It's a way of taking a basis for a subspace and turning it into an orthonormal basis. That's it. That's all. See you next time for the last lecture. Bye.